When we ended our ANOVA video, we talked about what's the next step. We found a significant ANOVA, but where are the differences? Let's follow up that ANOVA with what are called multiple comparison procedures. For a quick review, we conducted a one-way analysis of variance. We had 4 groups, different amounts of involvement with pedometers, with the idea being that as people engage in different amounts of support, they'll engage in differential amounts of physical activity. Remember, the null hypothesis was that the 4 means were equivalent, and the alternative hypothesis was that they were not equivalent. Here are our results. We found out that those 4 means were significantly different. The F value was 15, probability was less than 0.001, so we rejected the null hypothesis. And if we did that, if we go back up now and look at the mean values for those 4 groups, where are the differences? We have 4 means, but where are the differences? Maybe the first mean differs from the other 3, or maybe the middle 2 different from... How do we know that? Well, that's where the use of multiple comparison procedures comes into play.
There are many different multiple comparison procedures available, and in order to determine which one you should use, you need to answer 3 questions. The first question is, do you only want to make simple comparisons, or do you want to make complex comparisons? Simple comparisons involve only 2 means, mean A versus mean B, mean A versus mean C, so forth. Perhaps you would like to find the mean of A and B and contrast that with C. That would be a multiple comparison. For example, in our illustration, you might want to compare pedometer only with the other 3 treatments with some form of support, just to see if there's a difference between just the pedometer or the pedometer and some form of support. That would involve 1 mean against the mean of 3 other means. That would be a complex multiple comparison. The second question you need to answer deals with contrast-based or family-based. This is a little more difficult to explain, but basically it means, do you want each contrast to be compared at a given alpha level, say 0.05, or an entire family of comparisons at 0.05? The main difference between these is that the contrast-based is more powerful, the family-based error rate is more conservative. The third question is planned or post hoc comparison. Planned comparison means looking at your hypotheses, you may only want to test certain contrasts. But with post hoc, you can do all the contrasts possible. Some multiple comparison techniques are available only for planned comparisons, some for only post hoc comparisons. Here's an example of the answers to these 3 questions using Chaffee, Tukey, student-Newman-Cool's, and trend analysis. These are common multiple comparison techniques. Let's just take Chaffee, for example. Chaffee is both simple and complex contrast, meaning you can do multiple means or just 2 means. It is a family-based, and it is more conservative. In fact, it is the most conservative of all the multiple comparison techniques.
Family-based in the sense that all of the contrasts combined will have a probability of making a type 1 error of 0.05. So each individual contrast would have a much smaller alpha level.
That's why it's conservative. 2 of the most common ones are Tukey and student-Newman-Cool's. They are both simple contrasts. The difference is student-Newman-Cool's is contrast-based, where Tukey is family-based. Trend analysis is really not specifically a multiple comparison procedure, but it falls in the same family, and it's used when your independent variable actually is ordinal in measurement level, and you can use this to determine if there's a trend among the means. Do the means continually rise, or do they go up and then go down? You can determine whether the pattern of the means is linear, quadratic, cubic, or some other polynomial.
Returning now briefly to our SPSS output, we found there was a significant difference. Where are these differences? In one sense, this is referred to as an omnibus test or overall test. We know there's something going on. Let's go find out where it's going on. In our case, we'll use the student-Newman coils method. Here are the results, and in just a moment we'll show you how to get these with SPSS. Notice here we have the student Newman coils a contrast-based, simple contrast so that each one of these contrasts has a probability of making a type 1 error of 0.05. Notice that we have subsets of means. Any two means in the same subset are not significantly different. So notice under subset 1, the mean for pedometer only and pedometer and written support, those two means are not different from one another. In subset 2, the second mean and the third mean, 36,820 and 42,080, are not significantly different. And finally, in the last subset, the pedometer, personal, and computer support differs from all the other three. So on the right, you can see that are there differences between these paired means? 1 versus 2 is not significantly different. 2 versus 3 is not different. 1 versus 3 and 4, yes, they're different. 2 versus 4, yes, they're different. 3 versus 4, yes, they're different. We'll now turn to SPSS and illustrate how you can easily conduct multiple comparison procedures with SPSS.
Here's our very same data set again from the last video with the group membership in column 1 and the number of steps per week in column 2.
We'll first recreate the ANOVA output, that is the omnibus test. We go to Analyze, down to Compare Means, One-Way ANOVA. Our dependent variable is steps per week. Our factor is group. Remember the last time we clicked on options and we said descriptives. We'll continue. In this case, we want to also click on post-hoc procedures. So in our example, we used the student Newman coils. So we'll click on student Newman coils. Notice there are a wide variety of different post-hoc comparisons or contrasts that you might use.
We encourage you to play around with this sometime and just try and see what you get when you click on any of those.
So we'll continue and then say OK. Notice our output initially looks just like we had before. Here are our descriptive statistics. Here is the ANOVA source table, but now we get an extra piece at the bottom which presents the post-hoc procedures for student Newman coils. We've deleted the descriptive and ANOVA source table and just presented now the post-hoc comparisons with student Newman coils. And here again you'll see exactly the same output as we saw in the previous slides. So you can play around with various multiple comparison procedures, but you should plan before you do your study which ones you're actually going to use.